Okay, so I'm back. I'm assuming that you've gone through the Darth Vader scenario about who was Luke's father. So we will just continue on from here. All right, the next, we're going to just keep talking a little bit about these Punnett squares, but we're going to talk about a dihybrid cross now instead of a monohybrid cross. And a dihybrid cross is where you're analyzing two traits. So in this example, we've got an R trait and a Y trait, and we're crossing it. So again, these are going to separate into gametes. I'm going to switch over to my camera and I'm going to actually write these out. Okay, so let's see if I can manage to do this. I did it. Okay, so here was our cross. R, R, Y, Y. Okay, and R stands for round, if it's capital. The recessive trait is wrinkled. We're talking about seeds here. Capital Y is yellow, and lowercase y is green. Okay, so the thing to figure out here is that these need to separate into gametes. So this is going to split into either capital R or lowercase r when it gets distributed into gametes. So is this. So we need to figure out our gamete. So what's going to happen? That'll become a gamete. I think they call this foiling in math, but I'm not exactly sure. This will become a gamete, and then this will become a gamete. So they have to separate out from each other. All right, and the same thing will happen over here. And since that's actually identical, we'll just copy these down. Oops, that's a lowercase. Okay, so this dihybrid cross is done the same way. Figure out the gametes and then cross them. So I'll just get started here and you can see in very short order how this is extremely tedious. So that's a capital, that's a lowercase, etc., etc. So I will not make you watch me do this whole thing. All right, hold on. Okay, so I just finished filling in this Punnett square, the same way as before, and then you can sort of tabulate your phenotypes. So the round yellow ones, I would have 9 altogether. So that's going to be round and yellow, round and yellow. All right, all these red ones that I'm circling would give us a round yellow phenotype. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 of those. Round and green are going to be, this is going to be round and green, round and green, round and green. So 3 of those. Wrinkled in yellow will be wrinkled in yellow here, wrinkled in yellow, wrinkled in yellow. I'll have 3 of those. Scratchy throat this morning, sorry. And then wrinkled and green, it's going to be that one brown one. So we get this 9 to 3 to 3 to 1 ratio, okay? When we're crossing a dihybrid cross and they're heterozygous for both traits. Okay, but clearly that's extremely annoying. So there is a better way to do it. Which we should go through. Okay, so here's the results of what we just did. And that's the same answer. So there's a better way. Okay, so we are going to use some statistics to do this because, that's too much work. All right, and there's an easier way to do it. So we have to talk about probability here for a second. So if you flipped a coin 100 times, can you predict 100% certainty how many heads and how many tails you would get? Okay, so we're going to do a little review now on chi-square calculation. So if we did that experiment and we got 58 heads and 42 tails, is there a way to determine if it's close enough to be considered 50-50? Okay, so yes, you can do this with a chi-square calculation, okay, and you can be a certain level of confidence. So we really do need to do this. So this is really good practice, okay? So I will once again write this out for you on my camera, okay? And you should try it So pause the video and practice doing a little chi-square problem, okay? Because it's good practice, right? We did 100 flips of the coin. We got 58 heads and 42 tails. Okay, those are our observed. So I'm just going to make this table. So observed heads, tails. We observed 58 heads and 42 tails. If it was perfect, we would have expected it to be 50-50. Okay, so then you go observed minus expected. That gives you 8. That gives you -8. Obviously, you guys are better at math than I am, so you would probably just do this all in one fell swoop on your giant graphing calculators. Well, you know what? I need to do this way. So if you're bored, you just skip ahead. Anyway, all this comes out to this. Add that up. Get your sum, which is your chi-square, of 2.56. So now you got to compare that to your critical value. All right. So in this case, we had 2 cases. So n minus 1 is 2 minus 1 equals 1. So we have a critical value. And we look that up on our chart, and we get 3.84. That's at the 95% confidence level. Okay, so then you have to think, all right, am I going to reject or fail to reject? Well, in this case, 2.56 is less than 3.84. So we are going to fail to reject our null hypothesis, and this is due to chance. All right. Okay, sorry, I was having a little coughing attack. And I can't remember what I said before I stopped, but in any case, our chi-square value on this problem is less than our critical value, so we would fail to reject this. In other words, in this problem, the null hypothesis would say that there's no difference. 48 to 52 is not different to the expected 50-50, and we would agree with that, and we would reject the null hypothesis and say that this is close enough. Okay, so that's just a little mini review, but let's go back to our slides here, okay, and talk about probability. All right, so this problem is if you crossed a heterozygous purple flower with a white flower and you got 4 offspring, can you predict 100% for sure the genotype of each of the 4 problems? And I'm not going to write this one out for you. So I think you could do it, but no, you can't predict with 100% certainty. So we need to use, this is all about likelihood and probability. So the first probability rule we're going to talk about is the multiplication rule. And if you had AP Stats, maybe you know this already. If you didn't, that's perfectly fine. Okay, so the first rule is about what's the probability that 2 events will both happen, and it's equal to the probability of to the product of their individual probability. So you figure out the individual likelihood of something, and then you multiply it. Okay, so let's just do a problem, and these equations are on your equation sheet. Okay, so here's an example. All right, AA times AA, so heterozygous times heterozygous. What's the probability of getting a homozygous dominant? So clearly we could do this with a Punnett square, but let's do it using probability, and I'll show you what you do. So I am going to go back to here now. Okay, so the probability of this is our cross. Heterozygous times heterozygous. This is going to be the multiplication rule, also known as the AND rule. Okay, and we are trying to figure out what is the probability of getting an offspring that is a homozygous dominant. Okay, so here's what you do. You can figure out that from this parent, there's only one way to get that. So you'd have a 50% chance from that parent of getting that capital A. From this parent, there's also, a 50% chance of getting that. So the probability of getting that would be that probability times that probability. Okay, so you would multiply those together. So you would have a 25% chance of getting that. And if we did this in a Punnett square, let's just do it real quick, you would get the same thing. Okay, that. Okay, so 1 out of 4 likelihood that we would get this homozygous dominant offspring. Okay, so let's go back to here. All right, that was the multiplication rule. The other rule is called the addition rule. Okay, which is if there's more than one way to get an outcome, then you would add the probabilities of their individual likelihoods, or you would add their individual probabilities. So that, again, that equation is shown on your equation sheet. All right, and let's do another problem with the addition rule. Okay, so it's our same cross. Okay, and now we are going to see what is the probability of getting a heterozygous offspring. Okay, because there's more than one way that you could get that, which is why we need to use the addition rule. All right, so let me show you. All right, so now we're doing our same two parents, and we want to know what is the probability. That's a little hard to read, sorry. Probability of getting that. Okay, so there's more than one way to get that offspring from these parents. So in other words, let's start here. Okay, we could get that A with that A to get that offspring, or we could take that one with that one to get that offspring. So let's do this first. So let's do the first probability. From here, there's a 50% chance of getting that A allele. All right, and then from here, there's a 50% chance of getting that A allele, the little one. All right, so that would give us a fourth. Okay, the other way is here and here. So I'll just write this backwards, even though we don't normally write it backwards. And you get the same. So from this parent, there's a 50% chance of getting that allele. And from this parent, there's a 50% chance of getting that allele. So you have another 25% chance of getting it. Okay, so then you have to add those together. This is the addition rule. 1/4 plus 1/4 is 2/4, which is 1/2, which is a 50% chance. Okay, so again, we could do this on a Punnett square, this very simple one. In fact, I already did it right here. And we could see that we could get this or this. There's two different ways to get that outcome. So there's a 50% chance of getting that. So we have to think about the probability of each of the ways, and then you add those together. So that's the addition rule when there's more than one way to get an outcome. Okay, so I just did those with that Punnett square, which is pretty quick and easy. And why would we even bother using probability? Well, here's the problem. Okay, if you have a very large, or even a larger sort of cross, and you need to figure out the probability of a certain outcome, you would want to use statistics. Okay, so let's just do this real quick and I'll show you how you do it. All right, and then I think I'm going to have to stop, darn it. Okay, so here's what you do. All right, we've got our cross is between and we want to know the probability of getting this offspring. Okay, so I'm actually going to pause here for a second and write some of this out, and then I'll talk you through it. Actually, I'll just record while I'm doing it. So first of all, we're trying to get that. So there's only one way that we can get that, and that's if we get that allele from here and that allele from here. So there's a 50% chance from there, and there's a 50% chance from there. So that's 1/4. Okay, there's two ways to get this heterozygous part of that offspring. All right, we can get this with that. So that's what we just did. So we're going to have to use the addition rule. So the first way is 50% chance to get that capital Y, 50% chance to get that lowercase y, so that's that. Okay, but then we could also get this one, which is a 50% chance, with this one, which is also 50% chance. Okay, so that's a fourth. So overall, now we add those together, we have a 50% chance of getting this heterozygous at the Y allele. All right, and then here, there's only one way to get that. So we would use the multiplication rule. One way to get that lowercase c. All right, it's a 50% chance to get it from here. And it's a 50% chance of getting it from there. So that is a 25% chance. So overall now, to get this offspring, we would multiply those together. So 1/4 times 1/2 times 1/4 would be 1/32. So there's a 1/32 chance that we would get this offspring from those two parents. Okay, so that's why this probability business is very, very helpful. Okay, so I think I'm just gonna finish this little section here. I'm gonna keep going. All right, it won't be too much longer. All right, so let's talk about pedigrees real fast. Okay, this is a family tree and it shows the relationships between individuals. Okay, and here's what they look like. Males are always square, females are circles. If a male is affected by whatever it is we're talking about, it's filled in. A female's affected is filled in. When they mate, they have a line connecting them. And then whatever offspring they have come down. So let's look at a couple different pedigrees. This one's about widow's peak, so the thing on the forehead where your hair comes down in a pointy thing. We had a kid across the block from me when I was a little kid who had a major widow's peak, and we thought he was a vampire. So that's kind of mean, but sorry if you have a widow's peak if I offended you. Okay, so the question is this trait dominant or recessive? So if we sort of look through this pedigree, here's the first generation, second generation, third generation. Okay, and we can see that this affected individual right there has a widow's peak. Let me back up here. So if two affected individuals, so this one and this one, have an unaffected offspring, that trait is dominant. So in other words, if you look at this thing, you only needed one copy of that capital W to have that trait. So this person could be homozygous dominant or heterozygous, and she has that trait. This person doesn't have a single allele that's dominant, so she does not have it. So this is a dominant trait, okay? If you only need one copy to give you the trait, then that's dominant. The passing it on is dominant. Okay, here's another one about earlobes, whether it's dominant or recessive. So here's the generations. Okay, you can see this person is affected and their genotype is homozygous lowercase f, homozygous recessive. This person has a capital and a lowercase f, and they don't have it. Okay, and down here, again, the only people that are affected are the ones that have two lowercase f's. This person right here has a lowercase and a capital, and they don't have it. Okay, so this has got to be recessive. All right, if two unaffected individuals can have an offspring that's affected, then the trait is recessive. Okay, the other way to think about it is you've got to have two recessive alleles to have the trait, if the trait's recessive. Okay, so we'll probably do some more of those. I think there's on your homework. All right, and then this song is very, very hilarious. So I would strongly recommend that you watch that when you have a few minutes, okay, and see if you can figure out the pedigree. All right, I'm going to stop.